In this video, we're going to take a look at limits at infinity. So we've seen functions that become infinite when we approach a finite x value. But what about functions when we approach an infinite x value? What happens? And so as mentioned before, as we approach a very large x value, we get a horizontal asymptote in some functions. And horizontal asymptotes act like a barrier or a boundary that the function cannot cross. And so if we look at the arctangent of x, we see that as x approaches a very large number, so an infinitely large number, our function is approaching this line of pi over 2, but it never touches it. So we say that as x approaches infinity, our function is approaching pi over 2, even though it never truly gets there. Well, likewise, we can say the same thing on the left. As x approaches negative infinity, our function is approaching negative pi over 2. And so even though our function is never equal to negative pi over 2, at a negatively infinite x, we are equal to negative pi over 2, or we are approaching negative pi over 2. And so the definition of limits at infinity and horizontal asymptotes read that if f of x becomes arbitrarily close to a finite number L for all sufficiently large and positive x, then we write that the limit of f of x as x approaches infinity is equal to L. We say that the limit of f of x as x approaches infinity is L, and in this case the line y equals L is a horizontal asymptote of f. We can define negative infinity in a similar fashion and say the same thing about the limit existing and having a horizontal asymptote. In some cases, we can get this same limit as we approach from positive infinity and negative infinity, such as the function f of x is equal to 2 plus 10 over x squared. We see that as x approaches positive infinity, our function is settling at a value of 2. And we could even say it's coming to 2 from the right. It's above 2. And as we approach negative infinity, our function is also approaching 2, and once again it's also approaching 2 from the right. Now in algebra we may have the preconceived notion that asymptotes are boundaries that cannot be crossed, and I even alluded to that earlier in the video. However, that is not always the case. We can have an asymptote that is crossed. It can even be crossed an infinite number of times, such as the function f of x equals 3 plus 3 sine x over radical x. This function is oscillating about the horizontal line of y equals 3, but the oscillations, the waves are dampening and they're getting smaller and smaller as they go. And so the limit as x approaches infinity, as we go to larger x, we settle at a value of 3. And we can see this by taking the limit of just 3. Well, the limit of 3 as x goes to infinity is 3, and the limit of 3 sine x over radical x as x goes to infinity is 0. And we're going to look at that analytically a little further in a moment. But if these are our two limits, well then the sum of those two is going to be 3. So as x approaches infinity, our limit of our function is 3. Sometimes we can even have functions that have infinite limits at infinity, such as the cubic function y equals x cubed. As x approaches positive infinity, our function is approaching positive infinity. It just keeps going on forever and ever. There is no asymptote. There is no settling off of a value. It just continues to increase. Well, likewise, as we approach negative infinity, our function is approaching negative infinity, so it just continues to go on forever and ever. This behavior is consistent for all odd functions, and we see that with odd functions, as x approaches positive infinity, we approach either positive or negative infinity, and then as we approach negative infinity, we approach the other infinity. So if it's going off to positive infinity to the right, it'll go to negative infinity to the left. If it goes to negative infinity to the right, it'll go to negative infinity on the left. we say that if f of x becomes arbitrarily large as x becomes arbitrarily large, then we write that the limit of f of x as x approaches infinity is equal to infinity. And we can similarly define all the other infinite limits at infinity using this same verbiage. And so continuing on the even and odd aspect, for all polynomials that are even, we see that the limit as x approaches positive or negative infinity is positive infinity. We go up to positive infinity on both sides. And for odd, we go up into opposite infinities. And if by chance we have a negative or the inverse of these two functions, and that's the additive inverse, not the multiplicative inverse or functional inverse, but if we have the opposite of an even function, then we're going to approach negative infinity on both sides. And for an odd function, it'll be positive infinity on the left and negative infinity on the right.